Hello and welcome to Train Signal. You are watching Encryption Options. In our lesson on security administration, we touched on how important a role security plays in your responsibilities as a network administrator. But in truth, since many individual systems are hijacked and used to launch even bigger attacks, every user of every system now has that same responsibility. So it's upon us all to ensure that we are diligent about considering security in every aspect of computing. One of those aspects is remote communications. Just think of all the people who need to remotely connect to other systems. Besides network administrators, there are telecommuters or mobile workers who spend the majority of their time away from the office. And what about web developers who routinely need to log into client systems for updates? We could probably go on and on with examples, but the point is that in all of these scenarios, if you need to remotely connect to your Linux system, you should do so using the most secure means, and today, that is the Secure Shell, or SSH. So in this lesson, we'll start off with an overview of the Secure Shell, then move into how to configure both the daemon and client. Next, we'll talk about SSH access controls and logins that dictate who can log into the system. In addition to remote sessions, you may also want to enable the ability for your users to encrypt their email. So we'll turn the discussion to GNU Privacy Guard. This is the tool designed to encrypt your email. And finally, we'll talk about the process of encrypting and decrypting data. Let's begin our lesson with an overview of SSH on the next slide. With larger networks, chances are you won't always be able to walk right over to a server console and log into a system. So we needed a mechanism that would allow for remote access into our servers. Now back in the old days, that tool was Telnet. But there was just one problem. It was totally lacking in security. Anything you typed in, from passwords to commands, was clearly visible. And again, earlier on this wasn't such a problem, but navigating today's virtual minefield of security threats, Telnet is virtually unused and unseen in real production environments. That's because we now have SSH. This secure shell is an end-to-end remote login tool. Now this is a client-server system where you run the SSHD daemon on the Linux server you want to connect to, and you run the client on the remote client system. So in other words, as an admin, if you'd like to be able to connect to a server from home, you'd install the SSHD daemon on the server and install the client on your home computer. The main advantage that SSH has over Telnet is encryption. Everything from your password to all the data you transmit over the connection is encrypted using encryption keys. And SSH also incorporates FTP's file transfer capabilities. And for the times when you need to use other protocols, particularly those that aren't encrypted, SSH has tunneling capabilities. Does all this mean that someone still couldn't eavesdrop on your remote communications? Not at all, but it does ensure that if they do, the gibberish they receive will be useless. Of course, every tool has its downside, and for SSH, the problem is slower connections and a modest performance degradation, particularly if you're using a graphical application like X or an X application. You launch the program via two methods, and you should be pretty familiar with them. The first is the sysv startup script, and then the other option is the super server that we just discussed in our security administration lesson. It might be best to use the startup script to negate performance issues with launching from the super server. Now, as you might have guessed, there are several SSH servers, but OpenSSH is the most commonly used. And like other programs, if you need to make changes to the configuration, you'll need to restart the daemon with etc inet.d sshd space reload. We're going to use both our Ubuntu and Fedora test systems for demonstration purposes, so let's go over to the terminal and see if we have SSH installed by default. If not, we'll go ahead and install it. Let's go ahead and launch a terminal window with Applications, System Tools, and Terminal. Now from the command line, to check and see if we have SSH installed, type in sbin service space SSHD status. and hit enter. Now this tells us that the daemon is indeed running and has a process ID of 2241. Now if the program wasn't installed, we'd install it either using the GUI package manager or via the command line with yum install OpenSSH-server. And also, if we did find that OpenSSH was installed, but that the daemon hadn't been started, we could launch it with sbin service sshd space start. Now let's type in ifconfig space eth1. And eth1 you can substitute with your own Ethernet card, which might be 0, 1, 2, etc. And hit enter. And from here, let's make note of the IP address. So if you make note of that, this is something that we're going to use in just a moment. Now let's go over to our Ubuntu test system, which will act as our client, and make sure that the client software is installed there. Let's launch a terminal window with Applications, Accessories, and Terminal. And at the command type, let's type in which, W-H-I-C-H, space SSH. Now if you recall from our Managing User Resources lesson, which is the weakest of the search tools, but what it will do for us is to search our current path for the first occurrence of the command that we typed in, or SSH. So go ahead and hit enter. And in this case, it tells us that SSH is installed and located in user bin SSH. Now let's say we wanted to connect to our Fedora server system. For that, we use the SSH command, and we would type in SSH space, and here we'd have to enter the name of the user, and if you recall, we created a test user named Nancy in one of our previous lessons. So let's type in Nancy at, and here we enter the IP address that we just noted, which in my case is 192.168.56.101. SSH space Nancy at 192.168.56.101. And go ahead and hit enter here. This message says that the authenticity of the host can't be established, and that's mainly because we haven't connected before. It asks if we're sure we want to continue, and let's type in yes and hit enter. This next statement tells us that it's adding this host to our list of known hosts so that we won't get this warning message again next time that we try to connect. And now it's going to ask us for our user's password. You go ahead and enter your user password and hit enter. And the prompt tells you that you're now logged into your remote system. Let's type in the ls command. We see that we don't have anything necessarily created in Nancy's home directory, but that does confirm that that's where we are. Now if we wanted to, we could create a file. So type in touch, T-O-U-C-H. If you recall, that command will create an empty file. And let's call this ssh-test.txt. And hit enter. Now type in ls. And you can see that our file has indeed been created. Now let's head back over to Fedora really quickly just to verify. Let's go ahead here and log in as root with su. Let's type in ls space /home. And we'll see our user Nancy here. So let's type in ls space /home/Nancy and hit enter. And you can see the file that we created again, ssh-test.txt. Now let's head back to the presentation and talk about configuring SSH. When you install the OpenSSH program, you do get both the daemon and client software, even if they aren't automatically started. You can configure the server daemon with the etc ssh sshd_config file. But the good news is that most of the time you won't need to change a thing. The file format is mainly option followed by value. The options include protocol, which specifies the protocol level that SSH can use. and the only possible values are 1 and 2. Since 1 has been compromised, 2 is the preferred value. On some older clients, though, you may need to still use Protocol 1. The next option is Permit Root Login, which enables SSH to accept direct logins from root. And while the default setting for this is yes, the most secure option is to set it to no. Forcing login as a regular user first just adds another layer of security, as an intruder would need to know information for 2 accounts. Another option is X11 forwarding, which sets the tunneling features. If you want to be able to run X programs via SSH, this option must be set to yes. OpenSSH is a very complex program, and there are of course more options, but these are the ones that you'll be most likely concerned with. The client configuration file is etc ssh ssh_config, and this file specifies parameters for all SSH users on your network. But these settings can be overridden with a local SSH configuration file in a user's home directory. And like with the daemon, you won't often need to make changes to this file anyway. SSH works through the use of encryption keys. Each server and user system has a unique key pair, a public and a private key. Now these keys are linked so that if you encrypt data with a public key, it can only be decrypted and read if the receiver has the matching private key. When a connection is first established, each side exchanges public keys. And once this initial exchange occurs, clients retain public keys so the same exchange doesn't have to happen each time they connect. And this also makes it easy to see changes to the public key, which could be a sign that it's been tampered with. Since OpenSSH server startup scripts look for stored public and private keys, if it doesn't find them, it goes ahead and generates them. 4 to 6 keys are stored in etc SSH, and they're named SSH_host_RSA_key and SSH_host_DSA_key. Both of these are the private keys, and you'll also have the same file names with the -pub extension, which represents the public keys. Now some systems may also include SSH_host_RSA1_key and its associated public key with the same file name. Now if these files don't exist and you can't start the SSH server, you can generate the keys yourself using the ssh-keygen command. And there are 3 commands that you need to execute. The first is ssh-keygen --q --t --rsa1 --f etc ssh --host_key --C, and then you have a -N enclosed in 2 single quotes. You'd also have to enter the same command for the RSA and DSA keys. Now I do have to caution you not to run these commands if the files already exist on your system. This would signal to clients that you've already successfully connected with that something might be wrong and they might refuse the connection. Additionally, private keys should be treated with care. The whole system that SSH has created can be compromised if your private key falls into the wrong hands. Let's go back to the terminal and see if these files exist on our test system. Let's go ahead and clear the screen, and let's type in ls to list the contents of etc ssh, since that's where the files would be stored. And as you see, we have the host DSA key, the private key, as well as the public, and we've got the host RSA key, private and public pair as well. Now, if these files didn't exist, let's just take a quick look at the command that we would type to generate. We'll start off with the first one. It would be ssh-keygen --q --t --rsa -f etc ssh --host_RSA_key --C two single quotes, space, dash, capital N, space followed by a trailing two single quotes. Now again, this is the command that you would type, and you see that we have RSA here. You would do the same command for DSA. But again, since we already have the files, we're not going to execute this command because that would overwrite what we already have set. When configuring a client, another good idea is to create a global cache of host keys, also known as the known host file. And again, you can have a global file and you can also have an individual user file. The global file, which is ssh_known_hosts, is stored in either etc or etc/ssh. Your public key list is built from the sources you use to populate the global file. And as a side bonus, when your users connect to hosts whose keys you've included in the file, they won't get that confirmation message. You can create the file by picking an account that is already connected to all of the hosts you'd like to include in your global file. Then you can simply use the copy command to copy the file from the user's home directory to etc/ssh or etc. So for instance, if we use Nancy as an example, we could copy a file from Nancy's home directory to etc/ssh. The command would read cp space home nancy.ssh known_host space etc/ssh ssh_known_host. The file should include fields for host name, IP, or both, and then you also have the key type and the actual key. You add entries to this file not by modifying it directly, but by using the user's account to connect to the systems that you want to add and then reloading the file. Let's talk about SSH access control on the next slide. You'll likely want to limit who has access to your server via SSH, and there are many options to accomplish this. The first and easiest is through the use of usernames and passwords. From the demonstration that we did earlier, we know that the username is sent automatically as part of the command, and then the user is prompted for their password. In addition to passwords, you can also use TCP wrappers. Now remember that TCP wrapper functionality is included with super servers, inetd and xinetd. So if you use this method to launch OpenSSH, or if your server was compiled with support, you can use the etc hosts.allow and host.deny files to limit access using IP addresses. You can also use a firewall rule to restrict access to port 22, which, if you recall from our network configuration and troubleshooting lesson, is the port number assigned to SSH. And another option, if you recall, is the etc no login file, which can be used to restrict login access only to root. Though this isn't a configuration I recommend, there is a way to configure SSH not to require passwords. You can set up the SSH client with keys and give the public key to the server. The SSH client can identify itself, removing the need for you to enter a password. To set things up, you'd follow these steps. First, you'd log in to the client as the user who will be performing the remote access. Then you enter the command ssh-keygen-q-t space rsa space -f space tilde /.ssh/id_rsa space -C, and then in double single quotation marks -N. Then you copy the ID_RSA file to the server using another name. Then you log into the SSH server and type your password. Next, you add the contents of the file that you just transferred to the end of the authorized_keys file. You can do this with the cat command and the redirector by typing in cat space tilde temp.rsa, the double greater than sign redirector, then the target is tilde.ssh authorized_keys. Then if you log out and log in again, you shouldn't be asked for a password. If requiring a password every time you use SSH is too much, and configuring a no password login is far too scary, There is a middle ground. The SSH agent program requires a password to initiate the connection, but once this happens, it remembers the password so that you only have to type it in once per session. SSH agent might be enabled on your system, but if it isn't, to enable it, you just log into the client as a user who's going to be performing the remote access. Then you issue the command ssh-keygen -q -t -rsa -f -tilde .ssh id _rsa -c. Then again you copy that file id _rsa.pub to another name somewhere that we can get to it quickly. Then you log into the SSH server. Then you're going to use the cat command with the redirector again to transfer the file. And once you log out and log back in, on the client you type in ssh-agent bin bash and then ssh-add followed by tilde .ssh id _rsa. When you use SSH to connect to a remote system to which you supplied your public key, you won't need to type in a password, but you will have to repeat steps 2 to 3 when you log out. The SSH login script, or SSHRC, which is stored in either etc or etc SSH, is OpenSSH's own login script, and you run it using bin sh, which, if you recall, is a symbolic link to bash. This method simply means that the user's configured shell is replaced by OpenSSH's shell. SSH has the ability to transfer its encryption functionality onto other protocols. This is known as port tunneling. The way that it works is the server computer runs 2 server programs: a server for the tunneled protocol using the internet and an SSH server. The client also runs 2 clients, one for the tunneled protocol and also an SSH server. The SSH client also listens for connections for the tunneled protocol, meaning it is acting as both a client and a server. When the client receives a connection from the tunneled protocol's client, the result is that the tunneled protocol's connection is encrypted using SSH. It's tunneled to the SSH server and then directed to the target server. So data that passes over the network is in an encrypted form, even if the target protocol doesn't support encryption natively. This process is enabled by default, but can be configured via the etc ssh sshd _config file with the option allow TCP forwarding. It'll probably be set to no, and all you need to do is change that to yes. On the client, you establish a special SSH connection to the server by passing several parameters. In the example on the screen, the SSH command is followed by -N and lowercase f, which tell SSH not to execute a remote command and to execute in the background after asking for a password. This creates the tunnel. Next, the -L option specifies the local port on which to listen, the remote computer to connect to, and the port on the remote computer you want to connect to. So the command says SSH to test.ssh.com on port 143, don't execute a remote command, and ask for a password and run in the background. Once the tunnel is established, use the client program to connect to the local port specified by the first number in the -L parameter. Now that we know how to make a connection, what if we wanted to copy over some files? You use the command scp followed by the name of the file and the target system with an optional username in front. You end the command with a colon. So a typical command might read scp space test file space user@user.com followed by colon. Let's go back to our Ubuntu system and try copying a file. Okay, if you haven't already logged out from our previous command, go ahead and do so. And we'll see the connection is closed. Now let's see what files we have on the system. Let's create a file called scptest.txt. And again, we do that with the touch command. touch scp test.txt. And we can see our new file here. Now, using the scp command, let's type in scp space scp test.txt space Nancy, because we're going to copy it to Nancy's directory, Nancy at 192.168.56.101. And this is the same IP that we used earlier, as you can see. So we've got scp, that's the copy command. Then we've got the name of the file, scp-test.txt. Then we have the optional username at the IP address or host name. So let's hit enter. And it looks like nothing happened. Type in ls. And as you can see, we have a file that's called Nancy at 192.168.56.101. Can you guess what went wrong? If you guessed that we forgot to include the trailing colon, you're right. So let's use the up arrow key to bring our command back up and add in the colon. So our command reads scp scp-test.txt space Nancy, the name of the user, at the IP address followed by the colon. And hit enter. And in just a moment we should be prompted for our password. And we type in the user's password and hit enter. And we can see that the test copy has completed. If we now go over to Fedora, we can verify that the file was indeed copied. On our Fedora system, let's type in ls space /home Nancy. And we can see our new file, scp-test.txt. Though SSH is a program intended to enhance secure communications, there are things that you can do to configure it to be its most secure. First, you should set it to accept only Level 2 protocol connections and also refuse direct root logins. Again, Level 1 has been compromised, and forcing 2 logins adds an extra layer of security. So requiring a regular user login and then root login just requires an intruder to have an additional piece of information. The next thing that you should do is disable X forwarding if you don't need it. You can also use TCP wrappers or firewall rules to limit access from remote clients. After all, there's really no need to open things up to the entire world, is there? Next, be sure to update software when updates are available. Bug fixes address many security issues. And finally, be sure to protect your private keys. Set permissions on the keys appropriately and make sure that they aren't left lying around or in removable media. So we've secured our remote communications and even securely copied files. But what about our email? Many organizations not only encourage, but some even require email encryption. As sensitive customer information or other company data is commonly exchanged via email, this certainly makes sense. GNU Privacy Guard, or GPG, is an email encryption tool that also allows for digital signatures that can be used to verify your identity. This tool is a spin-off of Pretty Good Privacy. GPG should be included with your distribution, so all you need to do is to generate the public and private key pair. You sign messages with your private key, and recipients verify it with your public key. To generate your keys, you use the command gpg space ~gen-key. Then you'll have to answer some questions. The keys are stored in home under the .gnupg directory. Once created, you export your public key with gpg space ~export space email address space > space gpg.pub. This saves the public key associated with the name or email address that's in the gpg.pub file. Then all you need to do is make your key available to others so that they can encrypt messages that they send to you or use it to verify messages that you send out to them. You can add the double dash armor option to produce ASCII output, which may be good if you plan to email your public key. In turn, to encrypt email that you send to somebody else, you need their public key. You have to then add it to your key ring with the command gpg space double dash import space file name. Now, of course, it is possible for someone to try to impersonate you with a fake public key, so be sure to use a secure method when you send it out. And if you want to take a look at your key ring, you can use the command gpg space double dash list dash keys. The UID line in this file is most important as it contains the name and email address you'll use. Let's go to a terminal window and generate our GPG keys. So we've decided that we want to encrypt our email. The first thing that we need to do is to generate our keys. So from the command line, let's type in gpg space double dash gen dash key. So we've got gpg 2 dashes gen dash key. And let's hit enter. Now you'll have to answer some questions, and generally you can accept the defaults. And the information here is just telling you that it's going to create some information, a new configuration file. It's going to tell you that the key ring's created. Then it's going to ask you to select what kind of key that you want. I'm going to go ahead and accept the default, number 1, and hit enter. And it says the keys may be between 1024 and 4096 bits. What key size do you want? The default is 2048, so let's go ahead and enter that and hit enter. Then it says please specify how long the key should be valid. 0 is the default that says the key does not expire, so let's go ahead and hit 0. Then it asks you to confirm if this was what you want, and I'm going to hit Y for yes. Then it says you need a user ID to identify your keys. The software constructs the user ID from the real name, the comment, and the email address in this form. So it asks to enter your real name. I'm going to enter my name, and I'm going to make up a fake email address, vhenry@vhenry.com. Comment, just going to put in Linux. Then it says that we've selected this ID, Veronica Henry, comment Linux, and the email address vhenry@vhenry.com. You can either change the name, the comment, the email, or if everything is okay, you can use O, you can hit O or Q to quit. So I'm going to hit O for OK. Then it says that we need a passphrase. And go ahead and enter a passphrase of your choice. Should of course be something secure, but something that you can remember. Then you have to repeat it. Then it says we need to generate some random bytes. It's a good idea to perform some other action, type on the keyboard or move the mouse. During the prime generation, this gives the random number generator a better chance to gain enough entropy. Now it's telling me that not enough random bytes are available. Do some other work to give the OS a chance to collect more entropy. So let's go ahead and maybe launch a browser. Then perhaps we can launch another terminal window. Type in a few commands. Then if you check back, it'll give you an update as to how much more it needs. It says that we need 71 more bytes. So let's give this another try. Let's do some more work. Take a look at our train signal blog. And as luck would have it, we see an article from me. Lots of information on our train signal blog, so be sure to check that out from time to time as well. Now let's see what's going on in our window here. And finally, our public and private key has been created. Now if we wanted to export the key, we'd have to use the export command. Now let's type in GPG space -- space vhenry at vhenry.com space > gpg.pub. So again, we're going to export. We have the email address, the redirection to the file gpg.pub. And hit enter. And now that our public key has been exported, we could again take this and give it to people with whom we want to communicate via email. Now let's go back to our presentation and talk about how to encrypt and decrypt data. In addition to secure email, you can use GPG to encrypt and decrypt data. Say you wanted to encrypt a file, you use the command GPG space -- space name of the encrypted file space -- recipient space user ID space -- armor space -- encrypt space the original file name. Armor and recipient are optional, and you can get the UID from the GPG space -- list / keys command. Or you could also use the email address instead. If you haven't signed the recipient's key, you'll need to verify you want to use that key. The result is a newly created file as indicated by the name that you include for encrypted file. If you leave out the armor option, the file will be binary and you'll need to send it as an attachment if you email it. Including the armor option makes the output ASCII, which you can then cut and paste into an email or send as an attachment if you like. If you receive a file encrypted with your public key, you can reverse the encryption using the -- decrypt option, or GPG space -- out space followed by the decrypted file space -- decrypt space the name of the encrypted file. And you'll be prompted for your passphrase. Most email clients include options for GPG usage, so if you use a client, the process becomes even easier. To sign a message so the recipient knows that it comes from you, use the command GPG space -- clear sign followed by the file name. You can also use the -- sign option, which creates a new file with the same name as the original, but with the GPG extension. Clear sign leaves the message unencrypted but adds an encrypted signature. The signature can be verified with your public key. And the clear sign option creates a file with the .asc extension. When you receive a signed message, you verify the signature with GPG space -- verify space file name. GPG will display a good signature message. And to read the encrypted message, you use the decrypt option that we just discussed. And that concludes our lesson on encryption options. Let's review what we've learned on the next slide. We covered quite a bit of ground in this lesson. As remote connections have become a standard requirement for admins and your users alike, it's important that we don't overlook the security implications of not ensuring the data sent over these connections is encrypted. It's time to let go of unsecured protocols and embrace the protection offered by a new tool. So in this lesson, we started with an overview of SSH that talked about its origins and how it improves upon Telnet with its built-in encryption. Then we talked about SSH configuration, including file locations and the associated options. Next, we reviewed SSH access control and logins, and how firewalls, TCP wrappers, and the no login file can be used to restrict server access, and also, besides username and passwords, how to use the no password and SSH login options. We also discussed SSH security best practices, including things like not allowing direct root logins and protecting your privacy keys. We then turned the discussion to GNU Privacy Guard and how to use this program to encrypt email messages. We learned that GPG uses a similar public and private key pair to manage encryption. And finally, we talked about using GPG to encrypt files. Thanks for watching, and I'll see you in the next lesson.